Hi, how are you doing today? We are going to analyze and design concrete structure with eccentric footing using popular design softwares. The Staad for modeling and analysis, and Rcdc for design and detailing of reinforcements. We have a model here, a four-story residential building with roof deck and has a plan dimension of 8 meters length by 5 meters wide. You know guys, it's been very common nowadays that we buy a very expensive house lot of 150 square meters lot area, and there we may build our house for our living. So to maximize the space in this lot, like here, in the boundary of this lot, either from the right side or left side, we construct the firewall here and leave ample space to other side for a separate purpose. So that the building would look like this. Meaning, if we try to analyze the scenario, what would be its foundation look like? See, this is the rectangular lot. This is 12 meters and this is 10 meters here. And both sides here are owned by your friends and neighbor. So in the building code, we are allowed to build our structure here near the boundary as long as the structure starts with firewall here. There is totally no opening in this wall. We can provide ventilation opening of our house elsewhere. Building a house at the center of this lot would make space inadequate and unsatisfactory. Thus, majority of us like to build one in this area to maximize the space. So this is now the location of the building that we are going to analyze, and the footing would be like this. Footing can't be built beyond this boundary, so the column will be positioned here at the edge of the footing, while we don't have any problem in the other side. We will design the footing in such a way that all footings shall as much as possible not overlap with one another, and shall not occupy the space of the neighborhood. The structure is assumed to be located in Zone 4 with NA is equal to 1.2, NB is equal to 1.6. These are our load combinations for concrete design of columns and beams, including footing, and these are found in NSCV section 203.3.1 and 203.4.2. Now let us open our substructure file. And we are going to add these load combinations that I was referring here in the auto load combination manager in Staad software. Our columns and beams are already analyzed and designed by Rcdc software. But let us verify if the members are indeed safe. So I'll show you, but take note, columns here in the substructure must be either the same or greater in size than that of superstructure. So as you see guys, the members are okay. Now, what if we design the footings concentrically? What will be their sizes? Let us try to check before proceeding to our main goal of this video. So we found out the maximum size is 2.25 meters by 2.25 meters. So now let's proceed to eccentric design of footing. Since the left side footings are the footings to be centrically designed, then upward reaction exerted by the soil in every footing is in this location. If we cut a section in this side, since soil resultant reaction force is in this footing directed upward, then it will create a moment to the column directed counterclockwise. Therefore, we apply moment at this column and the direction is counterclockwise. We can assume a positive moment of 300 kN meter for every column where footing is eccentric. We can assume 350, 300, and 200. Or another way is to offset these columns by let's say 0.4 meters and then get the moment in the output. So we can have preliminary moment to use as an assumption. We can use this value here as an assumption, but take note, it should be positive. So to do this, go to loading, then did load. Highlight DL1 and click add. Click node in this portion and in MG, write 350, then click add. $300, add, then 200, add, close. Then assign this to this node. After this, run analysis. Check again the load if the direction is correct. Otherwise, we have to reverse its direction by changing the sign. If you can see the arrow of the moment applied, we can perhaps exit the Staad and reopen again. So as we see here, the direction is counterclockwise. Next, close the file and open the Rcdc software. Let us check first beams. Our reduction factor for shear is 0.75. In this example, I use 40 mm clear cover for beams and columns. This beams here fill, so we will increase size. Just right click and click design. After design, go to File and click Update Analysis File. Next, we have to open the Staad file to run the update by running the analysis again. After running the analysis, let's open again the Rcdc and check again the bin if it's okay. Let's check if we can reduce the size of every member. After this, we proceed to checking columns. Columns filled as expected. Right click and click redesign column. Now let us check again the column. Next, let's check footing. In the settings, general settings, which is important, we have to check the following. Consider overburden, surcharge load, which is 2.94. Check for sliding. Check for overturning. I add surcharge load equal to 2.94 for in this model. Slab on grade completely lies on the ground, so I consider this as my additional load. And the overburden is the weight of the soil lying on top of the footing. The software will use the depth of footing in calculating soil weight. And our net SBC is 200 kilopascal. Pounding depth is 2 meters. And this is used, as I said, in calculating soil weight. And this soil weight helps in sliding and overturning check. There is the possibility if soil weight is not enough, the footing size will increase. So watch out for the surcharge load, soil weight, and soil bearing capacity. We have to check also the location of the water table. It must be deep down below, so we assume here 8 meters. We assume footing thickness to be 500 millimeter. And for the offset of the footing, click this plan limits here. 300 millimeter is the minimum offset of column allowed in this software. To adjust the eccentric footing size, if this bigger than this footing, increase moment or else decrease moment until we get the target size of this footing. So let's do it. Let's open the Staad file, leaving this Rcdc open. So let's go to loading, load cases details, then did load 1. So from here, this footing is smaller than this footing. So meaning to say we are going to decrease the moment on the node of this column. So we have to decrease a little bit. So let's say for example, we will make it, just make it 330. And the next, this column, this footing is bigger than this footing. So since bigger, we have to increase the moment. Let's make it 370. Next is this footing, which can be seen here, 2850 by 2850, which is smaller, this one, 2950. So we have to decrease the moment here. So we have to decrease, say, let's make this 187. Or let's say 190. Then run analysis. Close the file, then from Rcdc, go to file, then new, click no. Then let's check the beam. We cannot go directly to the footing. It's 20, 25, max dia. Auto design. So the beams are okay. Let's go to file, then new, then let us check the columns. So C3 fails. Let's increase this one. Make this 700 by 700. So we can check if we can reduce other columns. So now go to file and update analysis file. Erase this old, then rename this new, then run analysis. After running, just close and then again open the Rcdc. So again, let us double check the column. So everything is fine. Go to file, click new, and let's go to footing design. I think this video is enough for this topic. Next video, I'm going to discuss about strap footing design. Thanks for watching, and if you like the video, please hit the like and share button, and please don't forget to subscribe if you have not yet subscribed to keep you updated of any upcoming videos. Thanks and bye for now.